Hello everyone, this is Brock Skaggs and I'm going to make this video as an introduction into the SolidWorks application. And so let's just jump right in. As you can see on my cover slide, I have this kind of toy made of that connects to building blocks. This is an actual example of a SolidWorks assembly. I actually have these connects at home, and I took a dial caliper and started modeling them all up. And I modeled each of those component pieces as individual SolidWorks part files, and then I brought them all together into an assembly there. And so let's go ahead and jump to the next slide. So what is SolidWorks? SolidWorks is an example of a CAD application. CAD is an acronym. It stands for Computer-Aided Design. And so one of the big things with CAD is you're trying to build these models inside of the software so that you have a very flexible environment to add and remove features, change dimensions of features, and actually develop what this part or component is going to look like before you actually physically produce it. And so SolidWorks isn't the only application that kind of fits within this space. Other examples I've got listed here are CATIA. Also, the company Autodesk has a couple different applications that fit into this space. So one is AutoCAD, another is Inventor. One I haven't listed here is Fusion 360. PTC has Creo as well. So there's multiple different applications that kind of fit into this same space. And so don't worry about the fact that, hey, we're just going to be talking about SolidWorks. A lot of the skills that you learn from using SolidWorks are very easily transferred to these other applications if you find yourself at some point needing to use Inventor or Creo or CATIA there. And so in this class, we're going to be definitely focusing on fundamentals. And so what we're going to do with SolidWorks in 121 is definitely work on developing your modeling skills. And so we're going to be modeling items in 3D, and so you'll model parts, then you'll put those parts together into assemblies, and then you'll also be making documentation in the 2D sense there as well, and actually making 2D views. You'll learn what orthographic projection is and how those views are constructed from your 3D models. SolidWorks has a very slick interface with that, so you're not having to draw line by line by line like you might be doing in AutoCAD, but it'll do a lot of that work for you. Other examples that I'll talk about in the second half of this presentation is this idea of, hey, after I get comfortable with modeling individual components or assemblies or systems, what can I then do at that point? And we talked about the design process. We talked about like the analyze stage of it. This is where the CAD part actually starts turning over into more of a simulation tool. So you can start running simulations to test the structural properties of your system, or thermal, fluid, or kinematic, basically talking about how it's going to deform possibly under given loads, or how it's going to heat up and cool off. Or if I've got fluids, what's the impact of the fluid movement on the thermal characteristics possibly. Or we talk about kinematics, how is this articulated thing going to move throughout its space. Also, you can do rendering aspects of it. This is kind of more toward kind of a marketing bend almost, as far as I want to create a photorealistic image of my part, like sitting on the desk. Maybe it's something that you would be marketing toward an office user, and so you want it on the typical desk environment where this thing is going to live in the wild, so to speak. And so you can also do that with inside of SolidWorks. A couple notes about SolidWorks. It is feature-based and parametric. So feature-based, one of the things we'll talk about there, as far as if I got a complex part that I'm trying to model, don't get intimidated by the fact that, hey, it's very complex, but start breaking it down into individual features, and then focus on, hey, if I make this feature, then I can make that feature, then I can make that feature, and kind of chain these features together till you get to the overall complex model that you're trying to make. The other part of this is parametric. Parametric is nice. It's something baked into SolidWorks. It allows you to make changes at various points in the definition of the part itself at any time. And so this is very flexible. And so you can go back, let's say 3 features back into the tree, make a change there, rebuild, and it rebuilds all the way down through the tree itself there. This has a lot of benefits to you as the designer, as the person doing the modeling. One thing you can really focus on at the very beginning is think more about, well, what is the shape is it going to look like? Is that a circular arc that comes tangent to 2 lines, and not have to really think about necessarily the size at the same time. You can always go back and fit the driving dimensions onto that shape in order to come up with that size. Another thing you'll hear us talk about in terms of SolidWorks, or kind of in the vocabulary, is this idea of design intent. And so SolidWorks has some tools in there to help you capture the design intent beyond just explicitly defining dimensions. And so some of these are geometric relations, where I can go in there into the sketching environment and say things like, well, I want these two lines to be parallel or perpendicular, or I might have something to be coincident, or a line and arc become tangent to one another. That's an example of capturing the design intent. Obviously, driving dimensions are ones that come to mind as far as when I say, hey, that circle has a arc, which is a radius or a diameter of a certain value. You can also get a layer of complexity underneath that and say things like, well, I want to have some global variables that I want to play with, and I want those variables to drive equations that drive the dimensions there. And so there's kind of various levels of complexity there. And so we'll explore some of those as we get to more advanced, kind of going from novice to intermediate levels of the software itself here. So with that being said, I've got a couple slides here talking about the different file types that you'll be using inside of SolidWorks. And so one of these is an assembly and a part. And so I'll go ahead and jump into an assembly here, and then from the assembly I'll go ahead and just open the part here called the base foot. And so this is an example of a SolidWorks part file. One of the things, if you're looking in File Explorer, you'll see files with an extension SLDPRT, which you can see here at the very top of the screen. Think of those as SolidWorks part files. They're files that are native to the SolidWorks application. And so this is a nice little foot. It's actually off of a scissor type jack from my vehicle. And so one thing to note about the part file is I've got a tree structure here on the left hand side, and this is very common. SolidWorks has a lot of tree structures in here, whether I'm looking at a part, an assembly, or even a drawing. In a part, that tree structure is holding a listing of features. This one's a little bit different than the ones we'll be using in 121 in the fact that it's a sheet metal part, but this idea of having a listing of features is all the same. And so I have a base flange, an edge flange, a cut extrude. And these are just showing the different features that I use to build this part. These flange features will be something that's specific to sheet metal. Something that we'll start off with in our 121 class will be things like boss extrudes and cut extrudes in order to start making our parts. And now after I create some part files, one thing that I can do is put them together inside of an assembly, which is exactly what we have here. Now just looking at the file type here at the top where it says the file name, it's an SLD ASM, so that's a SolidWorks assembly file. And so that's when I take all my SLD PRT files and I put them all together inside of a SLD ASM file. A couple notes that are worth mentioning here very early on, so don't worry about having to memorize all this stuff, but when you create these, the SolidWorks assembly file doesn't just kind of copy the information into itself, because you'd think if I did that, I'd end up with very, very large assembly files. But instead of copying, it basically finds references or paths. It stores the path saying, hey, if the assembly file is here, I'm going to go store the location of the part file, and that way I can go find that information and grab it as needed. So that is a very important thing to understand as you start working with assemblies. One thing you might ask as far as, hey, I've got a three-dimensional space here. How do I relate the position of the individual components next to each other? Well, that's in the mates. And so if you look at the left-hand side, we've got another tree structures. Now, instead of on a part, the tree structure holding features, most commonly in an assembly, the tree structure will hold component parts there. And so here's that base foot that we were just looking at. Then I've got a couple arm features that I have in the lower arm. It looks like they are different than the upper arms. The 1 and the 2 are the same part that I'm referencing, just different instances of it. I've got a top pad, some connector blocks here. It's like a spacer and a threaded rod. And then at the very bottom of this assembly, you'll see a node called mates. And this is where we're storing the relative position of each of the components to each other. So I say things like coincident, and here several times I've got a screw mate, some gear mates here as well. And so this assembly in this state is actually fully constrained. And what that means is I can't pull around and drag it. If you see, I try to pull the top plate up, it says the selected component is fully defined, it cannot be moved. So I've explicitly defined the locations of all the components here. But you might say, hey, this thing's actually supposed to move in reality, right? That's the whole point of this device, is to lift things. And so one thing I've done in this model is made it in such a way that I can take this initial condition, I can suppress it, so that means temporarily ignore, if you will, that mate. And now if I pull on this top plate, you'll see that it allows me to move the jack. And so I can move it up and down. I've got this thing modeled in such a way that that vertical plate can only move in a vertical direction. You can see right from this front view, I'm not moving it left and right. And one other thing to note about it is as I move it vertically up and down, you can see that this threaded rod is rotating one way, and then if I push it down, it's rotating the opposite way. And so this is one of the things I've actually done via a screw mate, is to model this relationship between the rotation of this rod and what would be the translation of these connector bits there. And so this is one thing you can do to actually mimic what this thing's going to do in real life. Say you knew the threads properties of the threaded rod, so maybe it's a 1/4-20 type thread nomenclature that you would use there, and then with a little kinematic knowledge you would know that, hey, for every revolution of the rod, the translation of the nut will be a certain value there. And so I can actually bake that into my SolidWorks model itself. And you don't really have to do any math there to figure that part out. That's part of what the software is doing there for you. You're just having to describe the properties of that mate to it. And so there's an example of a assembly. I don't have an example of a drawing with me, but I'll just show you a screenshot here. Example of a drawing, that is a 2D drawing of a 3D model that I had. It's just a simple gantry. It's actually made via weldments. But basically just the idea that, hey, I can take one of these 3D models, I can pull it into a 2D drawing environment, and I can create detailed component drawings. That's where I'd be describing like the dimensions of all the features so that I could have somebody fabricate that component, or I could make an assembly drawing. This is kind of like a top level assembly drawing in this case, where I've got different elements that would have to be fabricated, right? I'd buy different lengths of this material and I have to cut it in such a way that I can then put it together like this for possibly welding it together at that point. And so we'll talk about those also as we move throughout the semester. I did talk about the SolidWorks assembly, so we're good here. But I also wanted to talk about some of the things beyond 121. So we're in a very fundamental course here, MECET 121, just going to get your feet wet throughout the semester, get you comfortable with modeling. But there's more that you can do with SolidWorks beyond just modeling the parts in terms of just getting the geometry defined. And so let's talk about a few of those examples. My first one looks like is this example of the C-clamp. And so here again I'm looking at a SolidWorks part file, but I want to go beyond just modeling the geometry. This is an example of a part that's definitely going to be under load, right? As I use a C-clamp, I'm squeezing the object in the middle and it's pushing back against the frame of the clamp here. And I want to simulate that in the software. When I'm analyzing the design of this component, I want to be able to see if it's going to break or not under the given loads I expect to see in the field. And so one thing that SolidWorks has is SolidWorks simulation, and this is kind of an add-in module of SolidWorks which allows you to do this type of study. And so what I've done here is I've just said, hey, I'm going to hold this part right here, and these purple areas represent a force, and you can see there it's a force of about 108 pounds moving in the direction of those arrows. And when I say moving, I'm merely saying directed in that direction. And so what you can actually do is have SolidWorks run this simulation. You're saying, hey, if I hold it here, if I push on it here, if the material of this component is cast carbon steel, what's going to happen? And so then you can start to develop these plots. And so this process is known as FEA, or Finite Element Analysis, and it will allow you to simulate the performance of the material of the given component you're looking at. And so at this point you end up with this kind of rainbow colored plot, and it's what it's trying to do is show you the stresses, or how much loading, we'll say, is on different parts of the component. And I've got a nice legend here on the right hand side, and you can see the maximum stress in this direction, in the X direction, is roughly 10,000 psi. And if I look at the model, I can see that happens right here on the insides of these arcs. And so you'd say, okay, that's nice. I mean, if you knew some stuff about materials and mechanics of materials, you could see things like, well, is this thing going to be okay? Is it going to crack? Is it going to plastically deform under this load or not? Those are all things that will be covered in future classes. But as a design side of things, one of the things you might say is, well, once I get that value, if it's too high, what could I do? Well, I could change the radius of this arc a little bit. And so maybe that radius right now is, we'll say, 1/4 inch. Well, what happens if I change it to 3/8 of an inch or 1/2 inch there? That's definitely going to change the geometry, which also should impact the stresses that I'm seeing in that region. So that's another thing that you would do with SolidWorks after you create the model definition itself there. Now you start simulating what the loads are going to be on the model. Another thing that we can do is have mechanisms that move, and so SolidWorks allows you to work with that as well. So as an example of that, I've got this very simple mechanism here. It's a inline slider crank mechanism, so you can see I can grab a part here. This is a SolidWorks assembly, as you can see, and I've got individual components, one part here, and one part here. But I can grab this part and I can rotate it, and you can see the kind of square or rectangle just oscillates there to the right. And so we might pose some questions about, well, if I rotate this, we'll call it the crank, in a certain fashion, how does the square member here respond? And we can actually study that. And so this requires a little bit different package of SolidWorks. It's SolidWorks Motion for what we're going to see. But I can develop these motion studies, and then I can have it compute what that motion would look like under a given definition. So that's what I did just then. By hitting that button, it actually did the computations there. You might say, well, how did you describe the motion of that crank? Well, if I come up here, again, SolidWorks likes these tree structures. You can see in the lower left, I've got a tree structure here, and I've defined a rotary motor. And I can come in here and say, edit the definition of it. It's defined as an expression, so I can come in here and say, edit. And it looks like I defined it as far as the angular velocity of that crank in degrees per second as 25 times time cubed in this sense. So I gave it some sort of mathematical expression in order to describe the motion of that crank. And so that was kind of the input, but then after I run the simulation, I can actually pull information off of it. And so that's what I'm showing here. This plot number 4 is the linear displacement, so it's the position of any given instance of essentially the center of this circle with the center of this circle. The circle on the right here is going to move left and right in this perspective, whereas the center here of the crank is not going to move at all. It's just going to be rotating about that axis itself here. And so this curve represents the relative position or the distance between those 2 points as the mechanism went through its motion. Then we can start talking about kinematics of it as far as, well, if that's the displacement, if I take a derivative of that, that would give me velocity, and I could also look at the accelerations. You could essentially do that mathematically, numerically, with the data. Or you can also come down here and you'll see that I've actually got that in terms of different plots that SolidWorks has computed for us as well. Again, this is all part of the analysis part of what SolidWorks allows you to do after you create your models. And so that was a nice, very simple motion model, right? An inline slider crank. But sometimes you have things that are more complex, and sometimes you have things that have coordinated motion with each other. They get very difficult to do model that motion just with basic time steps. And so SolidWorks again comes to the rescue with that, and it has event-based motion. And so in this example here, I've got this platform right here, and I've got an elevator, and I've got these blocks A and B, and the whole idea is, hey, can I get block A on a certain platform and get block B on a different platform here? And I've left out any sort of actuators, but just to talk about the event-based motion side of SolidWorks, we'll look at this Motion Study 2. And so what I've got with Motion Study 2 here is a nice table down here. And what SolidWorks has allowed me to do is define the steps in this motion. So I'll go ahead and play it real quick, and I'll play it at, let's say, half speed. So as you can see here, I've got a step that's active, that's what's green showing, and it's saying, hey, move block A, and then take block A up and slide it onto that platform. And now notice I'm executing a motion simulation here, but I'm not having to explicitly use a timeline. I'm basically programming steps and saying, hey, after this event happens, then wait a little bit, then go to the next event, so on and so forth here. And so this becomes a very convenient way to define your motion problems. If they're very complex and I've got multiple bodies that are interacting with each other in terms of happening coincidentally, I've got one body moving while another body's moving while a third body's moving, and I want to keep track of all that without having to go back to a simple time step. And there, it completed. Also, just to point out, we also have the ability to do rendering, and so a lot of the ones I've shown you, I believe at this point, have had some sort of shading, right? But when I first model a part in SolidWorks, it doesn't necessarily have that type of shading. A lot of times they just come in this kind of flat gray appearance there, and so that looks kind of dull in some sense, in some aspects. And so one thing you can do is actually apply appearances to the individual model itself. So this obviously looks like a checkerboard or a chessboard, and I put some kind of wood grain type of appearances on the different faces itself here. And then you can take it a step further and actually do the rendering part. Also on this one, you can see that I've got a decal that I've placed, so almost as if I had made my own sticker and put it in that bottom right square of the game board itself here. Again, this is the whole idea of, hey, I've modeled something in this three-dimensional virtual world, but I want to make that look as close as possible to the way it's going to look outside of that world. And that way, when I go to talk to the decision makers of the project, I can give them a very good feel of what this thing's going to look like if they plan to pursue to go forward with the project. Another thing, just to talk about complexity, the SolidWorks assemblies that we're going to look at in this class are not going to be very big. We're not going to have hundreds of components, but SolidWorks does have the ability to support very, very large components here. Such as an example of that a little bit is this open source router project where there's hundreds of components inside of the assembly, but SolidWorks is still able to handle that level of complexity. And so that brings us to the end of our presentation here. Again, I was just hoping to get your feet wet a little bit with SolidWorks, kind of show the basic fundamental building blocks as far as what does a part look like, what does an assembly look like, what does a drawing look like inside of SolidWorks, and then give you a little bit of feel for, hey, this is kind of the first floor as far as modeling the geometry of SolidWorks, and then what can I do inside of SolidWorks to support other design activities as I'm using the software. And so with that being said, thank you for watching the video.